Hello everyone, welcome to a new lecture of our course on heterogeneous systems. Today we continue talking about GPU programming, and in particular we are going to introduce a new parallel pattern, histogram calculation. Histograms, as you may know, are extremely useful in many different fields such as image processing. Together with histograms, we will also talk in detail about the evolution of atomic operations over the architecture generations, because they are so important for the generation of histograms. Before we go into the details about the histograms, let me very quickly remind you what we covered in our previous lecture. We talked about another parallel pattern, the reduction operation. As you may remember, a reduction is an operation that reduces a set of values to a single value, and it uses an operator that might be addition, product, minimum, maximum. This operator needs to have some properties. It needs to be associative, commutative, and have an identity value. For example, in the case of addition, this identity value is 0. As you may know, reduction is a key primitive for parallel computing, for example, in the MapReduce programming model. Remember that we talk about how to generate, how to calculate a reduction. First of all, starting with a sequential reduction. In a sequential reduction, what we are going to do is obtaining a single value, the reduction result, from all the values of an input array. Let's imagine that we have an array of n elements. This will require us n iterations of this simple code where we go to the array, read the element, and accumulate in some accumulator. In this slide, this accumulator is called sum. The good thing here is that there are many independent operations, so it's possible to create a parallel implementation that can calculate multiple partial sums and then reduce them. In parallel machines, such as GPUs, for example, we typically use tree-based reduction. In a tree-based reduction on GPU, what we would do is dividing the input array into the available thread blocks, such as thread block 0 and thread block 1, and then internally we divide the assigned chunk to the thread block to the different threads or different warps, as you see. Then we are going to iteratively perform partial reduction operations where we will obtain some partial results that we keep in some temporary storage, such as shared memory or registers. At some point, we will need to synchronize, because threads from one warp may need to access values, partial results generated by threads of other warps, and that's what we are going to do with an intra-block synchronization, this sync threads function. We continue with the execution. Remember that in this tree-based reduction, half of the threads, half of the active threads retire when we go from one iteration to the next iteration. At some point, we will need to synchronize again. And finally, we will obtain a single reduction or partial reduction per thread block. After that, we need to do some sort of inter-block synchronization. Something that we can do is terminating the kernel and moving all the partial results to the CPU and then performing the final reduction on the CPU. Or if we have many of these partial reductions, what we can do is launching a new kernel, like in a recursive manner, to perform again the tree-based reduction on GPU. And another possibility is to use atomic operations in global memory. Because we have a single value per thread block, we could have one thread of this thread block using a global, an atomic operation to global memory and accumulating the final reduction result in some memory position in global memory. The way that we map the computation in this parallel reduction to the available threads might determine clearly what's going to be the performance of our work. For example, we could go for a simple naive mapping, such as this one, where we are only using even number threads, and from the start, we tell each of the even number threads to add two numbers, the number corresponding to it and the nearby number. And in the next, so we perform and accumulate the partial results and some temporary storage. In the next iteration, half of the threads retire, and we continue adding values and obtaining partial sums, partial reductions until we get to the final value. The problem with this kind of naive mapping is that it causes low SIMD utilization, and this low SIMD utilization in the end is going to cause low performance or bad performance. Why that happened? Because when threads start retiring iteration after iteration, observe that all warps keep active, but most of the threads remain idle in each warp, and that essentially causes a lot of warp underutilization or low SIMD utilization. How can we avoid this warp underutilization? We can try like a smarter divergence-free mapping where the active threads belong to the same warp or to the same warps. And in this case, what we are going to use is threads to perform the partial reductions. We are going to use threads that are consecutively numbered, and that means that they are going to belong to the same warp or to the same group of warps. And when they start retiring iteration after iteration, we will make sure that the remaining threads, the threads that continue being active, belong to the same warp. And here you can see the code with high SIMD utilization, and you can also see here in this figure how when from one iteration to the next iteration, half of the threads retire, those threads that remain belong to the same warp, and that increases the warp utilization significantly, and thus producing much higher performance. Another interesting observation here is that as we make progress in the computation, iteration after iteration, there is a point where the active threads only need to access partial values that have been generated by threads in the same warp. And when that happens, we don't need anymore to go to shared memory and use sync threads. Why is that? Because these days, newer architecture generations, GPU architecture generations, provide warp shuffle functions. These are especially intrinsics that enable threads belonging to the same warp to share data with other threads in the same warp. And this is going to be faster than using than using shared memory and sync threads, as we do in the initial iterations of the reduction operation. And there are different variants of these warp shuffle functions. There is, for example, this shuffle sync to perform a direct copy from the index lane. There is this shuffle up sync to get the value from a thread with a lower ID or from a higher ID, or based on a bitwise XOR of the own lane ID. And this is a code for the warp shuffle, the reduction with warp shuffle. Observe that in the very beginning, what we are assigning is an index obtained based on what's the block ID and the thread ID. Here we declare the space in the shared memory to perform or to accumulate the partial reductions. And in the very beginning, we have each thread already accessing two values from global memory, adding them and storing them in the corresponding location in shared memory. After that, we synchronize and we go to this reduction tree in shared memory. This is essentially the same code as we have seen before for the, let's say, efficient reduction operation with high SIMD utilization. Observe that in each iteration, half of the threads retire. We keep accumulating, storing in shared memory, and then synchronizing because we have to make sure that all the active threads have already stored the partial value in the shared memory before we go to the next iteration. But at some point, we will have only 32 values to reduce, and that's the case where that's the point where we can start using the shuffle instructions, because only threads belonging to the same warp, as you see, all those thread ID, all those threads with thread ID lower than warp size, that is 32. So all the active threads in this part of the code belong to the same warp, and there is where we can use this shuffle down sync in order to access the partial results generated by other threads in the same warp that are now stored in this variable that will be in a register. We read this value using, in this case, shuffle down sync and accumulate, and we don't even need to synchronize or access shared memory anymore in this inner loop. And finally, we will obtain a partial sum per thread block. We can accumulate this partial sum in an output array for either a later kernel call or a final reduction in the CPU, but we could also replace this accumulation here with a global, an atomic operation to global memory to accumulate the partial sums into the final reduction value in global memory. So a novelty with respect to, I mean, a recent novelty for the implementation of the parallel reduction in most recent architectures is that they incorporate a new instruction natively supported that is a warp reduce and allows us to get rid of this inner loop that is highlighted in the slide. So it only works for certain data types, for example, int, but if that's the case, then we can make use of this warp reduce intrinsic. As I said, it's available only in the two most recent architecture generations since compute capability 8.0 with the Ampere architecture. And what we are doing is substituting the inner loop here using shuffle instructions with this reduce at same that performs the final reduction natively using specialized hardware. So this is all related to the reduction. Remember as well that we introduced in a previous lecture the atomic operations. Let me very briefly remind you what they are and how we can use them, because we need to use them for histogram generation or histogram calculation with this, which is the parallel primitive that we are covering into this lecture. Remember that CUDA provides atomic instructions on shared memory and global memory, and they perform a read, modify, write operation atomically. Here you can see an example. This is an atomic add where we identify the pointer to shared memory or to global memory that points, this is a pointer that points to the atomic variable that we are going to update using the atomic function or the atomic operation. This is the value that we are going to add, and this is the return value. In the case of these atomic operations, they return the old value. There are atomic operations for arithmetic arithmetic operations, but also for bitwise operations, for example, and or and XOR, and also different data types. You can go to the CUDA programming guide for the whole list of atomic operations and data types. The drawback of atomic operations is that they may serialize execution when there are atomic conflicts. So for example, if we have two threads in the same warp that want to update two different memory locations in shared memory or in global memory, they can perform the update at the same time. They can perform this read, modify, write, which is atomic, but because there is no contention, they can do it at the same time. However, if they want to update the same value, either in shared memory or in global memory, what's going to happen is that the access needs to be serialized. The update is serialized, and this entails an extra latency due to the atomic conflict. We also discussed in a previous lecture that atomic operations have interesting uses, but different uses as well. For example, they can be used for computation. We consider that they are used for computation when we use atomics on an array, on the elements of an array that will be the output of the kernel. An example is the histogram that we are going to study today, or the parallel reduction that we cover in the previous lecture and just recap on it in the beginning of this lecture. But atomic operations can also be used for synchronization when the atomic operations are performed on memory locations that are used for synchronization or coordination or communication across threads. Examples of that are counters, logs, flags, etc. We are going to see some examples today, and we will see more examples in later lectures as well. Atomic operations are important for have a functionally correct program because they are used to prevent data races that may happen when more than one thread needs to update the same memory location. I'm pretty sure that most of you are familiar with data races, but let's very briefly remind everyone what data races are. A data race occurs when multiple threads access the same memory location concurrently without ordering, and at least one access is a write. These data races may result in unpredictable program output. Let's see one example. Let's imagine that we have two threads, A and B, and they are creating a histogram. They are updating some bins, and based on the particular this particular B that they are using to index these bins that as I said, maybe a histogram. So they access this array of beans, they load it into this variable, they put the corresponding value into this variable, then they increment. In this case, they obtain a new value, and finally they write the new value in the original position in memory, right? And you can observe that thread A and thread B are doing exactly the same computation, and these two threads A and B might belong, for example, to the same warp, and so they execute concurrently. What the problem that we have here is that if both threads have the same B, they will have to update the same location in the array beans. And if these array beans, these beans B is initially 0, the final value of these two codes executing concurrently on two different threads, the final value might be 2 or might be 1. It depends. As you know, the correct result would be 2, but if data race happens, then the result will be only 1. Let's see, let's say the two cases in this example. So this might be one case, this is another case. As you see, the difference between these two is that in one case, one thread executes these 3 instructions one after the other, and then the other one goes and executes the 3 instructions one after the other. They might be executing concurrently, or they might be executing like a few cycles of difference. And if that is the case, then as you see, first of all, one thread executes the 3 instructions, then another thread executes the other 3 instructions, and in these two scenarios, the final value will be 2. So the result will be correct. However, what may happen as well is that the instructions, as they are executed by the two threads, in this case, they may be interleaved. And if that happens, and observe that in these two cases, what is happening is that all threads, or the two threads A and B, are reading beans B before the other thread has updated bean B. So here is when thread A reads, here is when thread B reads, then they both update, and then they both write. So the problem is that because they both read the same old value, and both are incrementing this old value, in the end, both are writing the same result. And the same happens in this code in the lower part. So in the two scenarios and many other different combinations of how the instructions are executed over time, the final value of beans B will be 1, and then it will be wrong. So one way of solving this to avoid these data races is to use, let's say, to have access is essentially to create a critical section to ensure that it's going to be a mutual exclusion. And that's what we normally do in CPUs when we use locks or mutexes. So if we have different threads running on the same or different CPU cores, but they have to update the same array beans, what we can do is lock in the access to these array bean, and after performing the update, unlocking the access. Two different threads cannot be at the same time inside the lock, inside the critical section. So this way we prevent the data races. However, this idea of using locks is not really very good idea in SIMD processors because it may cause deadlock. The reason is that the different threads executing in a SIMD fashion are accessing at the same time. So they could be accessing the locks at the same time, and we should come up with some way of dealing with this and avoiding the deadlocks. We are going to see later today some of these ways of avoiding these deadlocks. But for now, if you want to see how a fine-grained multi-thread architecture uses mutexes, I can recommend you to take a look at the ABMEM PIM architecture. In ABMEM, the PIM cores that are called DRAM processing units or DPUs are fine-grained multi-threaded. So, and they can run multiple hardware threads, up to 24 hardware threads. You may want to learn about this architecture by watching one of our lectures, some of the lectures in our processing in memory course. For example, in this lecture 2, in this semester, we presented the architecture and of UPMEM PIM and the pipeline of this fine-grained multi-threaded core. The threads that run on this pipeline can use mutexes for concurrent read, modify, write operations in a similar way as CPUs do. You may want to learn more about this architecture, about how to use mutexes. If you take a look at our paper, there you will see that we have experimented with these mutexes. This is an example of how to generate a histogram, two different ways of generating a histogram, one of them using mutexes on this architecture. These are some of the experimental results that you can find in our paper. Atomic operations have evolved over time. The GPU ISA has evolved over the architecture generations. The syntax of the CUDA of the atomic operations doesn't really change. Probably the PTX, which is an intermediate representation and intermediate ISA, also doesn't change or doesn't change that much. Here you can clearly see that this is an atomic operation on shared memory performing an addition on unsigned int of 32 bits. But the assembly code, the machine code that really runs on the GPU has actually changed over time. In the, for example, in the atomic operations in shared memory, the three first CUDA-enabled architectures, Tesla, Fermi, and Kepler, use these kind of, like lock, modify, and unlock loop, where they perform multiple iterations until all threads of the warp had updated the corresponding memory locations. After Maxwell, the atomic operations start being, to shared memory, start being natively supported, as you see. And as you will see later, much greater efficiency and performance. We are going to talk in more detail about these atomic operations in shared memory and how they have evolved. But first, we are going to talk about the parallel pattern that is the most important topic today, the histogram calculation. So remember, atomic operations can be used for computation, can be used for synchronization. Histogram is a good example of how to use them for computation, but we already talked in our previous lecture about how to use them for reduction. Remember that I mentioned that there are 7 different versions of the parallel reduction in the CUDA samples. Very interesting exercise to go over all these 7 versions to understand the different optimizations that are applied and see how the performance of the code, performance of the parallel reduction greatly increases optimization after optimization. I mentioned as well that I modified 3 of these implementations to replace the tree-based reduction with just one atomic operation to shared memory, and actually we observed quite good performance results, especially in the most in the newest architecture that we had tested, that was Maxwell, and we saw interesting performance improvements over the original versions, and also a way of implementing the parallel reduction with fewer lines of code. So there are some advantages, and these performance improvement was due to the fact that atomic operations to share memory were greatly improved in the Maxwell architecture. But as I said before, we are going to talk about that later in this lecture. We did a very thorough analysis of the search space of parallel reduction with 85 different versions possible, and with compiler support for automatic generation of these parallel reduction using warp shuffle primitives, warp shuffle operations, and atomic instructions. This is a paper that we presented to the CEO 2019, and definitely a very recommended reading. So let's talk about how to compute histograms, but before we start discussing the parallel implementation of the histogram computation, let's recap on what's a histogram. Histogram is a frequently used computation for reducing the dimensionality and extracting notable features and patterns from large data sets. They are widely used in, for example, image processing for feature extraction, also used in fraud detection, and many other fields. In a basic histogram, what we do is going over all elements elements in the input data set and identifying what's the bin that we have to increment. That's essentially based on what's the actual value of the element that we are reading. So in a histogram, we are going to have, let's say in the default histogram, what we have is a number of bins that is exactly the same as all possible values, that the number of possible values that the input elements may have. For example, in image processing, if we are working on 8-bit images or images where the pixels have a depth of 8 bits, we can have in total 256 different values. So the size of the histogram in this case is going to be 256. So when generating the histogram, first thing to do is reading the element of the input data set, checking what's the value, and then based on that, generating what's the bin that we need to update. Each bin is a counter, or we can say that each bin has a counter associated. So what we do is for each input element, we identify the bin and then we increment the counter for that bin. This increment might be, or typically is adding one, but in some cases we may also add more than one. In the end, this is an associative and commutative operation, so we can perform it in different ways. The way of generating a histogram in a sequential manner is to go over all the elements of the input array, checking what's the value, figuring out what's the histogram that we need to update, and then update the corresponding histogram. In this case, we are going to generate the histogram for this sentence. I calculate a histogram, and the histogram itself is here at the bottom, where you can see all possible values that we can have in the letters of this sentence. If we do a sequential reduction, a sequential histogram calculation here, in the first iteration, we will have our thread go into the first element of the input array, identifying it. This element is I, so we go to the corresponding bin and increment. Then we go to the second character, in this case, say in iteration 2, iteration 3, iteration 4, and so on and so forth. The code for a sequential histogram function, or the sequential histogram function, as you can see here, is pretty simple. The only thing that we have to do is going over all the elements of the input array, reading one value, and then going to the corresponding bin of the histogram and incrementing it. After that, we go to the next element and we continue doing it until we have visited the whole input array. But what if we want to implement this in parallel? It's something that we can do, right? Because we can read many of the input elements at the same time, and then updating, why not, some of the bins in the output histogram. So let's assume that we have 4 different threads, because we want our parallel implementation to be efficient on GPUs. What we are going to do is, with these 4 different threads, they are going to access nearby memory locations in order to make sure that the accesses to the input array are coalesced. And now they start performing updates. So for example, thread 0 is reading this I from memory. So it goes and increments the corresponding bin I in the histogram, or thread 1 is reading one space, so it goes and increments the element in so the bin corresponding to the space, and so on. And this is the corresponding code to this parallel implementation. Remember that we are working with GPUs, so we have to create a GPU kernel that we define using this global qualifier. In the beginning of the kernel, we obtain one index that is based on the one index, that is the index that we are going to use to access the input array, and this index is obtained based on the block ID and the thread ID. So we go to the input array, read one value, and then update the corresponding value of the histogram. However, this code, even though it looks good and probably could be efficient, but is wrong. Why is it wrong? Because in some cases, in the second iteration, in some cases there might be conflicts, as we are going to see. But let's continue with our processing here. In the second iteration, the 4 threads go to the next four elements of the input array, and then they update the same position, the corresponding bins in the histogram. But now observe that these thread 0 and thread 3 have to update the same element in the histogram. And the problem is that this would cause an atomic conflict or a data race, as we know. So we need to use atomic operations here to make sure that the histogram is correctly calculated and our program is functionally correct. So what we do is modifying our wrong code with a correct code that replaces the increment of the being of the histogram with an atomic operation that performs an atomic read, modify, write to the corresponding being of the histogram, as you can see on the slide. But as I said before, the problem with atomic operations is that they may serialize the execution, and these might be extremely costly if these atomic operations happen directly in global memory. Why is that? Because global memory is DRAM, is off chip, and it takes a while to go, several hundreds of cycles, as you may know, to go to the global memory, bring some value, bring it to the core, update, and then write back. And here you have some simplified representation of that. Imagine that we have two threads that want to update the same location in the NRAM, in the DRAM. So there will be some DRAM delay to some latency to fetch the value from DRAM, from the global memory. Then there is a transfer delay over the memory channel, over the off-chip bus that brings the data to the processor itself, to the GPU. Then there is some internal routing, and then here in a few cycles we can perform the update. But then we have to write back, going through the internal routing, transfer delay over the memory channel, and then DRAM delay, the DRAM latency to write one element. And then we would do the same for the next atomic operation, maybe performed by another thread in the same warp, updating the same global memory location. As you see, very costly, because most of the time what we are paying is the data movement from bringing data to the processor, to the SIMD lanes, and then writing it back. Hardware improvements that happen over time, the Fermi architecture improved significantly the execution of atomic operations in global memory, because then it was possible to directly perform the atomic operations in the L2 cache. So in that case, we can significantly reduce these data transfers because accessing something that is in L2 is going to take way less cycles, like an order of magnitude less cycles than going to the off-chip DRAM. But still, this is costly because the L2 is still relatively far from the cores. It's pretty large, so the latency of its access is relatively high, and also we keep having serialization. So another additional way of improving the performance here is performing the atomic operations on shared memory. In those cases where we can modify our code such that instead of updating values in global memory, we update values in shared memory that is closer. But of course, this requires work from the programmers and modification of the algorithm, as we will see. So histograms, as I said before, are widely used in image processing. We may want to do some computation before voting, before updating the histogram, but essentially the simple code is something like this. We go to the input image, we read one pixel of the image, we maybe perform some computation, obtain some value, and then with this value, we index the histogram and update the corresponding histogram being. This will be the image histogram in a sequential manner. If we want to do it in parallel, we can do it as well. But as we know, we have to be careful because there might be conflicts here. And that's why we need to use atomic operations. And actually, these atomic conflicts are going to be pretty frequent in natural images when we are processing natural images, because natural images show some spatial similarity of the pixel values. And that here you see a very nice example in the forehead of this woman here. We see that all the pixels have very similar values. If we go directly to the exact values that we have in the pixels, we see that in some cases nearby pixels have exactly the same value. So what that means is that there's going to be an atomic conflict for sure, because probably we will assign threads of the same warp to read these pixels and to update the corresponding histogram bins. So there will be an atomic conflict and there will be serialization. And one way of dealing with these atomic conflicts is using multiple subhistograms. And that's something that we can do because in the computation of histogram, we are using an operator that is associative and is commutative. So we can generate multiple histograms, multiple subhistograms, and then merge them all or reduce them all. So that's something that, because now we have more bins that we can update, probably these two threads, this thread will go to one subhistogram, this thread will update the same bin but in another subhistogram, so we are avoiding the conflict. We are reducing the frequency of the atomic conflicts by using multiple subhistograms, and this optimization technique is typically called privatization. So in privatization is an optimization technique where multiple private copies of an output are maintained when and then the global copy is updated on completion. So after we have created the private copies, we merge them. As I said before, this is possible to do when we have an operator that is associative and commutative. That's the case in histogram, because we are using additions to update the histogram and has the advantages that reduces the contention, the atomic conflicts on the global copy. And also, if the output is small enough, we can have the private copies in shared memory. And as we know, accessing, updating the elements of the histogram, the bins of the histogram in shared memory is going to be faster because the access latency is significantly smaller than going to the global memory. So that's essentially what we are going to do. We divide the image for which we want to create a histogram into multiple chunks. We assign each of these chunks to different thread blocks, and then each of these different thread blocks are going to have their own subhistogram, hopefully shared memory, because shared memory is not too large, but probably is enough to keep a 256 bin histogram or even larger. So we create these local subhistograms, and at the end of the kernel, we perform a parallel reduction in order to obtain the final histogram in global memory. We can combine the privatization with another interesting optimization technique, that is coarsening. In this case, what we do is using a fixed number of thread blocks, a number of thread blocks that is large enough to occupy the whole GPU and keep all GPU cores active. But what these thread blocks are going to do is going over the whole image chunk by chunk of the image. For example, here in this figure, we see that block 0 accesses this part of the image, and then this part of the image, and then this part of the image, and so on and so forth. So in total, in this simplified representation, we could be using only 4 thread blocks. What that means is that we only need to create 4 subhistograms, that we only need to initialize one, and we will only have to reduce into the final histogram once. If we have more thread blocks, we will have more subhistograms, and then the final parallel reduction would be costlier. And here you can see the code for the parallel histogram kernel with privatization and coarsening. As usual, we start with the thread ID, the global thread ID based on the block ID, and the local thread ID. We are also going to use this stride, that is the total number of threads, and we declare the private per block subhistogram, and then we do some subhistogram initialization. This means initializing all the bins of the histogram with the identity value, that in this case is 0. After this is done, all the bins of the local histogram are equal to 0, or the private histogram are equal to 0. We synchronize, and now we can start executing the main loop, going to the input image or the input array, reading one element, every thread in the warp and every thread in a thread block reads a different element from the image and or the input, and then updates the corresponding bin of the private subhistogram. After that, after we are done with this main loop, we synchronize to make sure that all threads of the block have updated the corresponding bins of the histogram based on the input elements that they read. And after that, we will perform the final reduction, in this case, using directly atomic operations in global memory. So we perform this final reduction to obtain the final histogram in global memory, that is this histo array. So as you see, this optimization, this privatization and coarsening is relatively easy to use, and I'm going to show you some performance results later. You'll see that it really produces very good performance improvement compared to just having a single histogram in global memory and having to update all bins, the bins of this histogram always in global memory. But we can go even further in the optimization of the use of atomic operations for histogram calculation. We can use warp synchronous programming for atomic operation. Warp synchronous programming essentially means using warp shuffle instructions and other important primitives that work at a warp level. You're already familiar with warp shuffle instructions because I mentioned them in the beginning of the lecture. These warp shuffle functions allow threads of one warp to access data that belongs to threads in the same warp, and this is pretty useful for communication across threads. But there are other useful warp synchronous primitives. For example, this sync warp that forces the reconvergence of threads in the mask. This active mask that returns a mask of converged threads. Essentially, this active mask is going to give us a 32-bit bitmap corresponding to each bit in the bitmap corresponding to each of the threads in the 32 threads in the warp, and depending on whether these threads are active or not, the corresponding bit of the mask or the bitmap will be set or not. There is also these other two primitives here, all sync and any sync, that return true if all or any of the participating threads pass true. There is also this ballot sync that returns the mask of threads that pass through, or we also have this match all sync that returns true if all participating threads pass the same value, or this match any sync that returns the mask of participating threads passing the same value. So it's going to return a mask that will have 1 in the corresponding bit if the corresponding thread has the same value here as other threads in the warp. So by using some of these warp synchronous primitives, we can create what we call the coalesced atomic operation that can kind of performing a local reduction per warp or several local reductions per warp, and then updating a particular location in shared memory or global memory using an atomic operation. But good thing here is that we can use a parallel reduction instead of just serializing all the time in cases where we are going to have a relatively high conflict degree, or we're going to have multiple threads in the warp conflicting because they are accessing the same memory locations. By using these coalesced atomic operations, we can greatly reduce the latency of the operation. But let's very, very quickly take a look at this atomic add function that would be called by threads executing a GPU kernel. Observe that in a similar way as we do in the atomic operations themselves, we have a pointer to the memory element, memory position that we want to update, and we have this value that is the value that we want to add to this pointer. But we may have multiple threads in the warp that want to update the same memory position. So what we do is, first of all, obtaining an active mask to see what threads in the warp are really going to execute this atomic add function. And then we use this match any sync to create a mask for all threads that need to update the same element, either in shared memory or in global memory. So we are going to create a mask here that we are going to use later. Where? Exactly here. We call another function that is reduce warp. Maybe we could directly use a native reduce function that already exists, since Ampere. So we call this reduce mask, reduce warp with the active mask, that is those threads that have the same pointer to update, and each of these threads contributes its own value. We perform the parallel reduction here for all those active threads, obtain some value, and this is the value that one of the active threads is going to be in charge of adding to the corresponding memory location that is pointed by this pointer here. In this case, using an atomic add, because we may have threads in other warps that want to update also the same memory location. Observe that the way to identify what thread is going to execute this atomic add, we use this first bit set. I don't exactly remember this FFS, what it means, but it's like the first bit that is set in the active mask. So that is the bit with the lowest index that is active, and if one particular thread identified by this lane is that bit that is active with the lowest index, then it goes, this is the one that is designated to update the corresponding location in global memory. And finally, the only thing that we need to do is using this shuffle sync just for the other active threads to read this value, that is the return value of the atomic operation, read it from the lane that performed the update. So we are for now done with how to calculate histograms in parallel using GPU, how to use atomic operations, how to alleviate the cost of atomic operations with privatization, also combined with coarsening. And finally, we have even seen a way fancier way of creating more efficient atomic operations with these codeless atomic operations that essentially check what are the active threads that need to update the same memory location, perform a partial reduction, and then use the atomic operation with the value obtained from this partial reduction. So as you see, there is a plethora of ways of optimizing the use of atomic operations, essentially because atomic operations are costly. And they are costly because they serialize the execution. And that's something that programmers know, but also hardware designers know. And because of that, the hardware and the architectural support for atomic operations has evolved in a very interesting way from the very beginning of the GPU computing era. And we are going to spend a few slides talking about this evolution of the architectural support for atomic operations. We are actually going to start with shared memory. Remember that atomic operations are possible in global memory and in shared memory. Let's start with the atomic operations in shared memory. You're already familiar with this. This is the syntax in CUDA. This is the corresponding instruction in the PTX, this intermediate representation, and then in the SAS or assembly code, depending on the architecture, we may have different instructions or different combinations of instructions to execute the same operation, in this case, an atomic operation. As I mentioned before, in Tesla, Fermi, and Kepler architecture, there was this loop that we are going to discuss in detail, but as you see, requiring 4 instructions, and also there's a branch instruction here. What that means is that this loop might be executed several times, And as a result, we may have cases where the latency is pretty high, as we will see, because we did some micro benchmarking. Since Maxwell, we have native atomic operations in shared memory, at least for certain data types and operations. But let's first talk about this lock-free mechanism for shared memory atomics that existed from Tesla to Kepler architectures. This is a patent that explains this lock-free mechanism. As you can see here, we can identify this is a GPU core. Inside the GPU core, we have the shared memory. And if we take a closer look at this shared memory, we see that the storage resource, that is the memory array itself, is accompanied with this memory lock unit that contains some lock bits. And this memory lock unit with the lock bits is going to be in charge of executing this lock-free code correctly. Let's talk a little bit more about these lock bits. You already know that shared memory is an interleaved memory or bank memory organization. This is bank 0. As you see, bank 0 has elements. We are assuming here, by the way, that there are 32 banks in shared memory. So this bank 0 contains address 0, 32, 64, 96, and so on, but also this address 1024, 1056, 2048, and so on. So as you see, the distance between these addresses is 32 because we have 32 shared memory banks. So this is bank 0, and these are the remaining 31 banks, as you see. So associated with these banks, there are some lock addresses, and in total, in the Fermi and Kepler architecture, we found out that there were 1024 different lock addresses and different lock bits. So what that means is that each of the lock bits is assigned and corresponds to multiple memory addresses. In particular, for example, this lock bit 0 is going to be used to atomically update this address 0 or address 1024 or address 2048 and so on and so forth. And actually, if we take a closer look at the addresses themselves, we can see that part of the bits of the address are going to be used to identify the bank, to address the bank, to address the row in the bank, or to address what we call a page. A page is essentially 1024 shared memory location, consecutive shared memory locations. So this would be, for example, address 1056 is in page 1. It's in this row 1, and is also in bank 0, as you see. And if we check, for example, address 0 is in page 0, row 0, and bank 0, or address 32 is in page 0, row 1, and bank 0. Observe that all these three are in the same bank. So if we want threads in the same warp access, for example, just a read or a write operation, access these three addresses, we would for sure have a bank conflict, and we know that bank conflicts serialize the execution. Unless we have more than one port per bank, it's not possible for two threads running concurrently to access memory locations in the same bank at the same time. So we have some serialization there, but also observe that if the row bits also match between two addresses, is not only the bank, but is also this row. What we have is that the two addresses are sharing these 10 bits, and what that means is that they also share the corresponding lock address and the corresponding lock bit. And we will see what are the implications of this. But before that, let's take a look at the assembly code for the shared memory atomics pre-Maxwell architecture. As I mentioned before, it's a lock-free mechanism that is based on predicated execution, and it needs to use 4 different instructions. The first one is this load and lock operation that perform a normal load from shared memory, a shared memory read, but also tries to lock the access to the corresponding shared memory position by acquiring one lock bit. If the lock bit is acquired by a specific thread, then this predicate register will be equal 1. And because this for loop is based on this lock-free mechanism is based on predicated execution, the execution of the next instruction is predicated to this P0 predicate bit. So if this is 1, then the integral addition will be executed, and then the store operation as well. And it's a store and unlock. So it writes the value obtained after the integral addition, and then unlocks the corresponding lock bit, so that is free and available for other warps that want to update the same memory location. Those threads that could not update the corresponding position because they were not able to acquire the corresponding lock bit have the opportunity to branch and start again this lock-free loop and try again to update. So the way that the lock bits are mapped to addresses in reality is linear, as we have seen 2 slides ago, but in principle that could be replaced by a more sophisticated hash function. And that's something that we actually tried, and we are going to see how we did it in a few slides. But as you see, that's essentially like recapping on what we have just covered. Let's imagine that we have this warp access pattern. We have these 32 threads belonging to the same warp that want to update these addresses in shared memory. If we check what are these memory addresses, we see that some of these, there will be some conflicts for sure, because some of the, let's say, bits 11 to 2 are the same for several of these addresses. Like, for example, these indicated by the blue arrows or the red arrows. There are conflicts there. So what that means is that there is contention when trying to acquire the lock bits, and that's going to make that the accesses are serialized and the execution of the atomic operations is serialized. Here in this slide, you see a very detailed execution timeline. We can identify in the warp access pattern that we have clearly an atomic conflict because these thread 0 and thread 4 need to update the same address 0, but we also have thread 1, 5, and 6 that want to update addresses that reside in the same memory bank. Like also these two, thread 2 and 3, these two are also going to update memory addresses, memory locations in the same bank. So we are going to see how this is resolved by using this lock-free mechanism. So very first thing, all these threads belong to the same warp, so they all together go to execute this load and lock instruction. What happens is that not all of them can, let's say, perform the memory accesses at the same time, because we have bank conflicts, and also some of them are contending as well in the access to the lock bits. So for example, what happens here is that because address 0 and address 32 are in the same shared memory bank, or address 1 and address 33 are in the same shared memory bank, we have a bank conflict, so we cannot access these two until these other have been already accessed. Same thing happens here with address 1024 and also with address 1056, because all of them are in the same shared memory bank. Also observe that there are some atomic conflicts due to some threads that want to update memory locations that are sharing the lock address and the lock bits. For example, these address 0, and address 1024. So for sure, only one of the 3 threads will be able to get the corresponding lock bit, lock that memory location for itself, and update that memory location. So those threads, for example, in this case, we assume that it was thread 0 that got the lock bit. So thread 0 can perform the predicated addition, same as other threads that don't have any conflict. And then after that, storing into the global memory the value obtained after the addition, and unlocking and releasing the locks. And then the execution of the branch instruction for those, in this case, 3 threads that could not acquire the lock in the lock unit. So as you see, all these entail some base latency, but there are additional latencies due to in this case, the bank conflicts. And now we're going to have even more extra latency because some of the threads will need to execute the loop again, right? For example, here, for threads 4, 5, and 6, 4, 5, and 6 go to shared memory again to read the corresponding values in the corresponding addresses, and also try to acquire the lock bits, and then perform the predicated addition for those who really were able to acquire the lock bits. In this case, we are assuming that are thread 4 and thread 6. So then they perform the store operation and release the corresponding lock. And same as before, there are some atomic conflicts in this process because these, for example, address 0, 1024, and 1056 belong to the same bank. So there are bank conflicts there, and we have to pay that extra latency. And in the end, in the final iteration, is only the final active thread is 5 that already now can acquire the lock bit and perform the predicated addition, the predicated store, and just simply doesn't execute this branch instruction because there is no need to go again and try in this lock-free mechanism. So here you see the detailed execution timeline for this implementation of the atomic operations, and we really analyze that with a lot of detail using different micro benchmarks. This is one of the micro benchmarks that we use. Observe that we are using this clock function that returns the cycle count, and we are repeating the atomic operation multiple times in order to average the measured latency and obtain more reliable results with our micro benchmark. What we did in this micro benchmark based analysis is to change the values here in this input data in order to change the warp access patterns, in order to change the amount of conflicts, atomic conflicts, bank conflicts, or even lock conflicts, as we will see that we are going to find when executing this code. So for example, one experiment that we did was changing the number of position conflicts. So here we call position conflict when we have 2 or more threads that want to update exactly the same memory address. And what we did, we changed the pattern such that the number of threads updating the same memory location was increasing, and that's what we call an n-way position conflict. So if we have n threads that want to update the same shared memory location, we have an n-way position conflict, and we changed the degree of the conflict from 1 to 32. So here in this case, if it's 1, there are no threads colliding, there is no conflict. If n-way is 32, means that all 32 threads of the warp want to update the same shared memory location. So every time that we increase the position, every time that we increase the number, the conflict degree, or the number of threads updating the same shared memory location, we see that the latency of the operation increases. And actually it increases in fixed steps of 120 cycles on the architecture that we use for our experiments. We also did a different experiment. Instead of producing position conflicts with the pattern in the input array, what we do is producing bank conflicts. So in this case, what we have is every time that we increase the conflict degree, what we have is 1 more thread updating a memory location in the same bank, but not necessarily the same memory location as others. So it's like, for example, if we have a single thread updating a memory location in bank 0, this thread updates address 0. If we have a two-way bank conflict, the second thread, the second conflicting thread is going to update address 32. If there is a three-way bank conflict, then the next thread is updating address 64, and so on and so forth. So as you see, we have bank conflicts, but there are no position conflicts here. So what we observe is that the latency increases as we increase the conflict degree, but in this case, the gap between these two consecutive points is 32 cycles. Why is that? Because there is no really position conflict. It's only a bank conflict that will happen in the load operation and in the store operation, but we don't need to repeat this loop of the lock-free mechanism. However, if we change this stride and we make it larger, for example, 256, what we observe is that every time that we have 4 more threads conflicting in the same bank, we also see that there is like a larger gap that is indicated by these arrows. And this larger gap is what we call the lock contention or lock conflict. That happens because after having, because in this experiment, the stride is 2056. So if we have 4 threads accessing the same bank with a stride 256, that means that they are already using 4 different lock bits. If we add 1 new thread to collide in the same bank, this thread will be accessing address 1024. And remember that address 1024 is sharing the same lock bit, the same lock address with address 0. And that means that we really have an atomic conflict because these two are sharing the lock bit. And that's what causes that we have these larger gaps from time to time. So this is all the characterization that we did to understand how the atomic operations in shared memory work in Tesla, Fermi, and Kepler architectures. And one of the key issues why this happened is because the hash function that connected the memory addresses with the lock addresses was very simple function. It was just like linear assignment. So one thing we could do is using configurable hash functions here to change the hash function, and depending on the workload, map the addresses to the lock addresses in a different way in order to avoid bank conflicts. And we experimented with this. A potential hash function that we could use is this XOR-based hash function. As you see, what we are doing to obtain the lock address and the bank address is to XOR different bits of the memory address. Based on that, we can reduce significantly the number of bank conflicts and atomic conflicts. These figures here, these graphs here, should look very familiar to you because they are essentially the same thing that we have seen in the previous slides. This is a M-way bank conflict with the strike 32. Observe that this line here that actually is experiments on a real GPU, but also on a simulator GPU sim. As you see, they match pretty well, and they also match pretty well with the experiments that we have discussed in the previous slides. This is the similar results for bank conflicts with the strike 256, but remember that there are also lock conflicts here. That's why the final the larger latency here with the highest M-way or 32-way bank conflict is larger than here. And this green line in the two plots represents the latency obtained after having used our XOR-based hash function. And as you see, there is a huge reduction of these latency. So that could be an efficient way of optimizing the execution of atomic operations on shared memory by modifying with minimal modifications to the existing hardware by using, let's say, smarter hash functions here. That could, as I said, be configurable for different workloads as well, and depending what are going to be the access patterns of these workloads, use different hash functions. That's something that we explored in our paper published and IEEE Transactions of Computers in 2016. So yeah, that's more or less how the atomic operations work in shared memory. Based on that understanding, we were able to propose an optimization to go even further in the histogram computation. The key idea is to continue using private subhistograms, but instead of using one single private subhistogram per block, we could use multiple private subhistograms per block. Of course, depending on what's the size of the histogram and what's the available shared memory. So the idea is that instead of using one subhistogram per block, as I said, we can use, for example, 4. And in that case, what we would do is if we have 4 threads of a warp that want to update the same shared memory bean, what they are going to do is updating the bean in different subhistograms. So for example, thread 0 updates here, thread 1 updates here, thread 2 updates here, and so on and so forth. Good thing is that avoids the position conflicts because we are updating beans in different subhistograms, but still we have the issue, and that's quite normal because the number of lines that we have is 32, and the size of a histogram is also typically a power of 2, like 256, or in this particular slide, we are considering subhistograms of 32 beans. So there are going to be, so in case that we have an access pattern like this, there are going to be bank conflicts and there are going to be lock conflicts as well. So one thing that we could do to avoid these conflicts is to use some padding. As you see, we leave here some empty memory locations such that we shift the mapping of the subhistogram on the shared memory. And this way, if we have these 4 threads that want to update the same being in different subhistograms, they are also updating it in different shared memory banks and with different log bits. And that greatly improved the performance of the histogram computation on the older GPU architectures. These are results for Fermi and Kepler with 100 natural images. Here we computed different histograms of size 64 and size 256 in this particular example, and we changed this replication factor or number of private subhistograms per thread block from 1 to the maximum possible number of subhistograms or privatized histograms that we could fit in the shared memory. In the case of a histogram size of 64 beans, up to 189 subhistograms per thread block. In the case of 256, up to 47 subhistograms per thread block. Remember that we are using not only this replication of the privatized copies, but also we are using padding, and you can see how much the execution time reduces as we increase the this replication factor, producing a very interesting performance improvement. The thing is that for Maxwell, the hardware itself improved greatly because atomic operations started to be supported natively by the hardware. And what happened is that we don't need anymore to try these fancy optimizations using multiple subhistograms per thread block and so on. As you see in Maxwell, represented the results by this green line, there is essentially no change in the performance, regardless of whether we use 1 subhistogram in shared memory or 47 subhistograms in shared memory. As you see, pretty interesting that the performance remains completely flat or almost completely flat, the execution time, because now we have hardware support that efficiently executes the atomic operations in shared memory. And even have another example, a string compaction is a atomic operation based string compaction. What we do here is just having a single counter per thread block, is just one single memory location per thread block that is updated by all threads of the thread block when they need to perform the string compaction operation, and observe that even with all threads of the thread block accessing the same shared memory location and updating atomically the same shared memory location, the execution time only increases from 0.33 to 0.77 in the case where we have the maximum, say, a degree of atomic conflict. And you can compare the executions on the Maxwell architecture to the execution on the Kepler architecture and see how greatly the new hardware improved the performance of this string compaction in this particular example. I don't have any figure representing these atomic units near the memory banks in the shared memory of NVIDIA GPUs, but something pretty similar already exists in AMD GPUs. This is like a figure from a white paper from the GCN architecture from 2012, where we can clearly identify these atomic units near the memory banks in the equivalent to the shared memory in AMD GPUs that is called the load data share. Atomic operations have also evolved greatly on their execution to on global memory. For example, in the Tesla architecture, the early G80 architecture from 2006, atomic operations were executed on DRAM. That means that every time that we wanted to execute an atomic operation, we had to go to the global memory, fetch one value, bring it to the core, perform the increment, for example, or the addition, and then write back to the DRAM. So that was extremely costly. In Fermi, as we mentioned before, the performance was greatly improved because the atomic operations were executed in L2 using atomic units near L2. And in Kepler, there is a further optimization in the hardware because these atomic units incorporate a sort of local buffer that even saves some accesses to the L2 itself, and thus producing significantly better performance. In Pascal, there were even more architectural improvements with support to 64-bit floating point atomic add as well. So this is like we're going to take a quick look at these atomic units near L2 with a local buffer. I'm not really sure if the actual implementation is the one that is explained in this patent, but it's probably something pretty similar. Here you can see that the L2 is divided into multiple partition units. Inside each of these partition units, we have the array itself of the memory array, the L2 cache, and then we also have these ROPs, raster operators is the meaning, and these ROPs are the atomic units that are that execute atomic operations near the L2. Here we can take a closer look. This is the partition unit. This is the L2 cache, and here we have the ROP. So if we take a even closer look at the ROP, we can see here an ALU to execute the operation itself, for example, an addition, and here we can identify the local buffer. So a good thing of this hardware is that if we have two threads executing concurrently, and when they want to update the same global memory location, and assuming that these global memory location, these global memory values are already in shared memory because we have brought the cache to the L2, I said shared memory and I meant L2. So we bring one cache line to the L2, so the caching is already in L2, but now we have two concurrent threads that want to update the same location in this local cache, in this cache line. So the two threads start the, send their command to this ROP, this atomic unit near the L2, and the first one will update the corresponding value in the LU, but they store the value, the result in this local value, in this local buffer for the next thread to take the value from the intermediate result from this local buffer, feed it to the ALU, perform, let's say, an addition, and so on and so forth. So we may have the 32 threads of the warp wanting to update the same memory location. This memory location is going to reside all the time in this local buffer. So the access to it is going to be much faster with a way reduced latency, even significantly shorter latency that reading the cache line or reading the element from DL2, because we are reading from even a closer local buffer, and the overall latency of the atomic operation is significantly reduced. We ran some experiment to understand how the atomic operations to global memory evolved from Tesla to Maxwell architecture, and to do so, we run an experiment where we apply two different parallelization patterns. The computation is exactly the same, but in one case we are using a scatter parallelization. In the other case, we are using a gathered parallelization. Observe that the input and the output arrays are exactly the same. We have exactly the same number of threads. The difference between these two approaches is how we distribute the computation over the available threads. In the scatter parallelization, we assign one thread to each element of the input array, while in the gathered parallelization, we assign one thread to each element of the output array. And what that means is that for every single thread in the scatter parallelization, after reading the element from the input, this thread needs to figure out what's the effect of the corresponding value of the input on all the different values of the output. So after reading this element 0 of the input array, this thread 0 should go and update this element 0 of the output, element 1, element 2, element 3, and so on and so forth. And that's the same for all the threads. And in the gathered parallelization, the way that we assign threads to the computation to the threads is the other way around. Here we are assigning threads to elements of the output array. So each thread needs to figure out what's the effect of all the elements of the input array, what's the effect of all the elements of the input array on the assigned output element, as you see. So what's the key difference between these two implementations? As you can see, there is no contention in the access to the output here, where we are going to update these output elements frequently, while in the scatter parallelization, there is going to be contention for sure. And this contention, the only way of resolving this contention and having a functionally correct program is to use atomic operations. And that's what we can see in our example codes. This is a code corresponding to the scatter operation. Remember, we are assigning in the scatter parallelization, we are assigning input elements to the threads. So each thread, based on the block index and thread index, we obtain one index to access the input array. Then we perform some computation that is out invariant, obtain some intermediate result, and with this intermediate result, we go over all the elements, these num out elements of the output array. We go over all the elements of the output array, obtain another partial value here with this out dependent, and update the corresponding memory location, the corresponding element of the output array using an atomic operation. We need to do that because we will probably have multiple threads of the input, multiple threads that have been assigned different elements of the input, but they all have to update all elements of the output. And that's why we have to use atomic operations here. However, in a gather approach, what we are doing is assigning to each thread one element of the output. So every thread only needs to worry about its own element of the output, but needs to go over all the elements of the input, these num-in elements of this input array. So we read every input, every element in the input array, obtain some intermediate result, then obtain some output dependent intermediate result, and then we update the corresponding element in the output array. And as you see, we are accumulating this outreg that comes or is produced by all the elements of the input, but in the end, the corresponding thread just needs to update its own element in the output. So that's why we don't need to use atomic operations here. So how about the evaluation? We run some experiments. Here you can see execution time for the different versions, the scatter and gather. The difference between these two versions of scatter and gather is that we are changing the access pattern and the way that the inputs affect the outputs in a way that here in this experiment, there are no atomic conflicts, while here the number of atomic conflicts is significantly larger. And also the number of atomic conflicts increases with the size of the input arrays that, no, actually this is the size of the, this is the size of the input arrays. So the larger the input array, we have more threads in the scatter approach, we have more threads trying to update the same memory locations corresponding to the output arrays. And we run these experiments on the Tesla, Fermi, Kepler, and Maxwell generations, and we see kind of very interesting results here. In the case of the Tesla, the oldest GPU architecture, because there is no well to cache and the execution of atomic operations happens in DRAM, we see that when the conflicts start increasing, the execution time also increases dramatically. But now we zoom in into this plot in order to check the results for the other architectures as well. We see that even in the case that there are no conflicts, because we have to go to the global memory very frequently, we see that the latency or the execution time in Tesla is pretty high. Even in Fermi, where we have already atomic operations in the L2, we have atomic units in L2, the execution time increases a lot when the number of conflicts starts increasing. Of course, this is much lower execution time than the execution time corresponding to the Tesla architecture, but it's still way higher than the execution time for the gather parallelization. But we go one step further, and now we see that in Kepler, there is a buffer in the atomic units in L2. So that's why we managed to reduce the execution time, even when we have conflicts for the scatter approach compared to Fermi and compared to Tesla. Even some more performance improvement in Maxwell, probably also due to higher frequency of the cores as well. But as you see, the interesting observation as well is the distance between the scatter approach and the gather approach also gets reduced over time, also gets reduced as the architecture and the hardware keeps improving. And let's say that the good thing is that with the architectural and hardware improvements for the atomic operations, it might make sense to start using atomic operations more because they are relative, so they are quite intuitive. And as we have discussed as well, for example, for the reduction operation, we can make programmers' life easier by writing less lines of code or avoiding fancy optimizations such as these multiple private subhistograms that we used once for the histogram calculation. And the effect of hardware improvements is something that we can see as well. This is a 256 beam histogram of 100 natural images. We are comparing here the performance of a shared memory-based implementation of the histogram calculation with one private histogram per block. We're comparing it to a single histogram in global memory. And we see that the execution time for the shared memory-based implementation was way lower in Fermi. However, because in Kepler, there was an optimization, a hardware optimization of the atomic operations in global memory, but not in shared memory. Interestingly, the execution time was quite the same in both implementations. However, in Maxwell, the hardware of the atomic operations in shared memory also improves due to these native atomic operations and shared memory. And we see how, again, the execution time reduces significantly. And again, it really makes sense to use one privatized histogram in shared memory instead of a single histogram in global memory. So this is all for today. I think it was a pretty long lecture because we covered the evolution of the atomic operations as well. I hope that you found it interesting. If you want to learn more about the histogram calculation and atomic operations, you can take a look at this chapter 9 in the book, Programming Massively Parallel Processors. This is all from my side for today. I hope you come back to these lectures on heterogeneous systems. We will continue next Tuesday with another parallel pattern. Thank you very much for your attention.